Okay, this is our project 3 for Ansys Fluent. We're going to be simulating flow around a cylinder. We're going to actually do this simulation 5 times using 5 different Reynolds numbers. I have set up the geometry and the mesh for 4 of those Reynolds numbers, and I'm going to perform the geometry and mesh for one of them. And our Reynolds numbers are going to be 0.5 for the first Reynolds number, Reynolds number of 40 for number 2, Reynolds number of 50 for 150 for number 3, Reynolds number of 50,000 for number 4, and a Reynolds number of 500,000 for 5. So let's get started with the first one, Reynolds number of 0.5, and we'll start with the geometry. New design modeler. And we're just a 2D XY plane is what we'll go with. And we'll sketch our circle here. Our circle is going to have a diameter of 1 meter. 1 meter right there. And we have to draw a box around our cylinder, but we're going to make some reference lines first. And each one of these reference lines are going to be 25 meters. We're going to make a 50 meter by 50 meter box around our cylinder. 25 meters here, 25 meters here. Okay, and here's our box, and we will use constraints, midpoints. Since we made it 25 by 25, we'll midpoint here, and there's our 50 by 50 box. Okay, we will remove our reference lines. So we have no more use for them. Okay, concept, surface from sketches. Click on the outside box, apply, and generate. And there is our cylinder. Okay, we will go back to Workbench and we'll start our mesh. It always takes a second. Oh, it didn't work. Go back to Workbench, retry mesh here. And this time it worked. Okay. All right. Start our mesh. Let's insert a method here. Click on face, apply. We're going to use triangles for this particular mesh. Generate. Let's go into sizing here. We got to move this over so we can, here we go. And we are going to click on our edge here. There we go. Apply. Our element size, we'll go number divisions 200. And then we will leave our curvature on and generate. Okay. Let's add inflation here. Click on the face, apply, geometry. Let's click on the edge of our cylinder here. Edge, we will first layer thickness. We'll define our height 0.003 with maximum layers of 65. And we'll generate on that. Next, we will, let's see here, we're going to make our element size 0.15. And we will generate with this. We have a nice mesh circle going. This setting our element size 0.15 should give us a full mesh for our entire square around our cylinder. And this takes a second as well. There we go. All right. And here's our mesh. There's our mesh around our cylinder. Here's the mesh that's all within. It looks real nice. Okay, we're going to name our boundaries here. This is our velocity inlet. And this will be our velocity outlet. Oops. We will name our two, top and bottom, our symmetry. And last but not least, we'll name the edge of our wall here, our cylinder R. We'll name that wall. Okay. Okay. Let's go back to Workbench. Let's update our mesh. And everything looks good here. Cancel this out. And let's go to Setup. Click Double Precision. We're going to pick 4 solver per processes and start. This takes a little tiny bit here. So you have a Reynolds number of 0.5. We're going to start off with our models. 0.5 is very laminar, so our viscous model here, we're going to change it to laminar for our materials, fluids, air is what we're going to be using. The flow will be air. Our density is just going to be 1 kilogram per meters cubed, and our viscosity is going to be 0.05 kilograms per meter second. 0.05 kilograms per meter second. Change, create, and close that out. Our boundary conditions, we will have a velocity inlet. We will edit our velocity here, our airflow velocity. It's going to be 0.025 meters per second. Extremely slow. This is to keep our Reynolds number very low. And close that out. Okay, we will go to reference values. We will come from velocity inlet. Here you can see our area, our density, our depth, our length. Our velocity is 0.025, our viscosity is 0.05. Those look good. We'll go to methods. Second order upwind. Second order coupled looks fine. Report definitions. We want to report our drag forces. So force report, drag coefficient. I do it all in the wall. Print to console, and okay. Close. So now we have our report definitions here. Let's go to initialization. More settings. We're going to do 25 iterations here. Okay, and initialize. Okay, and now our calculations here. Just for time's sake, we're going to do 500 iterations and calculate. Even at 500 iterations, it seems like it's low. Of course, my computer has had a quite the workout this week. So staying very linear at zero, it seems like. It's not moving around at all, which is okay. Our Reynolds number is extremely low. I think for the next four, we'll do 100 iterations because we'll be here all day. There. Okay, calculations complete. Okay, let's go look at our definitions. Let's go to our report here. We're going to compute this, and you can see that we have a drag coefficient of 16.09. And we'll go to our reports here. Forces, look at our forces. Let's print this out. Okay, here's our net forces. We have a drag force of 0.005, extremely low. Newtons. That is in newtons. Okay, let's come up here. Let's get out of here. Let's go back to Workbench and let's look at our results. There we go. And over here, let's look at our streamlines first. Start from velocity inlets, all domains. We're going to go with 500 points here and apply. Unexpected error while refreshing paying property. Now, this is what our streamlines look like here. Let's see if we can put some vectors in here. And location, symmetry 1, do factor, fly. And here's what our vectors look like around our flow. Very, very laminar, very slow. It's just creeps around our cylinder. Let's look at our contours here. Let's shut these off. Um, Contour, case, symmetry one. Let's look at velocity and 750. Apply. Okay, very, not a lot going on there. Let's look at our pressure. Why? Okay. Yeah, once again, not a lot of pressure, not a lot of movement there. Okay, let's move on to the next one. For this next one, we are going to have a Reynolds number of 40. The geometry and the mesh have already been performed on it, so we'll go right into setup and double precision and start. Okay. Okay. So again, for our model, it's going to be our viscosity is going to be very laminar. We have a Reynolds number of just 40. And our material, we use air again. Our density of air is going to be 1 kilogram per meter cubed. And our viscosity is going to be 0.5 kilograms per meter second. And we close that out. Boundary conditions. Get our velocity inlet. I'm going to edit this. We're going to have a air velocity of 20 meters per second. Meters per second. We'll apply that. Close. Okay, and then our reference values. Compute from velocity inlet. Everything here looks good. There's a velocity. Okay. Now we will report our definitions. New, report our drag forces from the wall at the console. Okay. I do want to look at our methods again. Second order upwind. These look good. Okay, and initialization. More settings. Let's go to 25 again. 5, okay. And, oh, whoops, we have to initialize here. Initialize. And run our calculations. And we'll do 500 again, except for I'm going to pause the video while this iterates. And we'll be right back. Okay. And our calculation is complete. So, okay, let's look at our definitions. For definitions, let's go to compute. Okay, you can see we have our drag coefficient of 1.532. Let's look at our reported forces here. We have a wall. I'll print these out. Okay, and we have a drag force of 306.467. All right, let's come over here. Let's go back to Workbench and let's look at our results. Here we go. Let's look at our streamlines. And we will go from velocity inlet. So again, we use 500 and apply. And here you can see our streamlines. Pretty good. Let's throw some vectors in there and really see what's going on. Symmetry 1, velocity and apply. Wow. Let's get this thing squared back up here. You can see some rotational movement inside. You have circular movement here, circular movement here, and you can see how it all comes right back in and moves around. According to our sheet, that's how it's supposed to be, circular and circular. Right there, that's Reynolds number equals 40. Let's look at our contours. And we will go with symmetry 1, velocity. Well, let's do regular velocity here. And we'll do 500. Apply. Let's turn off our vectors. And there's our velocity contour here. Not bad. Let's look at pressure. And apply here. Well, the pressure seems to be at the front of the cylinder, which would make sense. That's where the air is hitting it. All right, let's go to our next one. Let's go back to Workbench here. And we'll move on to our next Reynolds number. We have a Reynolds number of 150. Again, the geometry and mesh has already been made. So let's go to Setup and Double Precision. We're here, let's start. Okay, once again, Reynolds number of 150. We are still laminar for our viscous model. And our material will again be air. We will have an air density of 1 again. And this time our viscosity will be 0.33 kilograms per meter squared. Change, create, close. Let's go down to boundary conditions here. Velocity inlet, let's edit this. And this time we will have a velocity of 50 meters per second. And apply. Close. Okay, reference values. Here we go, from velocity inlet as usual. These all look good. Velocity 50 meters per second. Velocity 0.3333 kilograms per meter second. That's fine. Let's go to methods. Those all look good. Report definitions. Yes, we want to report our drag forces again on our wall into console. Okay, and we will do initialization. 25 iterations here. Okay, initialize. Okay, and then we will run calculations. Again, we'll do 500, but if it takes forever, I'll pause the video. 500 iterations, calculate. It seems to be taking its time. I'll pause the video and calculations are complete. Okay, let's go and look at our report definitions here. And we will compute. And we have a drag coefficient of 0.941. Let's look at our reported forces here. And on our wall, print. And it seems we have a drag force of 1,176.296 or 3 newtons right there. Okay. And let's get out of this here. Yes. And we'll go back to Workbench where we'll get our results. And let's see what we got here. Okay. Let's look at our streamlines. Okay, from velocity inlet, 500 here. And apply. And you can see things are getting a little more turbulent. With a Reynolds number of 150, you can see the red. Let's add some vectors in here. See if we can't see where these streamlines are going. And you can see, again, we have movement here. We have movement down here, swirls, where the whole streamline seems to come around here, come all the way back through and come back out the backside here. We have a lot of turbulence up here. We have, seems like, yeah, these are our alternating vortexes right here. Very cool. Let's look at our contours. Symmetry 1. Let's go with velocity here first off. We'll go 750 and apply. And it doesn't look bad at all. Let's turn off our vectors. There it is. Okay. And let's look at our pressure. Pressure contour. Still, once again, right in the front. Very little pressure behind. Okay. Let's move on to the next one. Let's go back to Workbench. Let's go to our fourth one with a Reynolds number of 50,000. Double precision. Oops. Or let's start it up. Okay. For this case, we're going to have a very low viscosity. Our model, since it's external flow, and we have a Reynolds number of 50,000, it's still considered laminar. So for our viscous model, we'll still use laminar. For our materials, we'll go back to air again. It's our flow material. Again, density is going to be 1 kilogram per meter cubed. Our viscosity is going to be 0.0006 kilograms per meter squared. And change, create, close. Let's go to boundary conditions again. Velocity inlet, edit. We're going to have a velocity of 30 meters per second. Why? Let's see. Okay. Reference values. Again, from velocity inlet. Everything looks good here. Methods. Everything's still good, second order. Okay, let's go to report definitions. Yes, we would like to report our drag force on our wall, coefficient drag. Okay, close, initialization. Again, 25. Okay, initialize. And run calculations. 500 again, calculate. And you can see it's starting to get a little wonky out here. But it'll straighten out, I imagine. We'll pause the video because this may take quite a while. Okay, and you can see 10 minutes later, we're just at 98% here. And you can see how our graph is going here. Calculations complete. Okay, let's go look back at our report definitions here. And compute. Okay, and we have a drag coefficient of 0.72 right here. Let's go back and let's look at our reports, our forces on the wall. Let's print it here. And we have a drag force of 324.285. Okay, let's go back to Workbench. Let's look at our results. Look at some streamlines and contours here. And here we go. Okay, first thing, streamlines. And let's go from velocity inlet. Let's do 500 here. And apply. And you can see our streamlines once again getting a little bit more turbulent out here on the edges. Let's add some vectors in there. Symmetry 1. Okay. And apply. Wow. Okay, we got all kinds of crazy vector stuff going on here. You can see here our wide turbulent lake behind our cylinder. All kinds of vortex rotational movement right here. Let's go look at our contours. And let's go with symmetry 1 here. I like to look at my velocity first because I think that's the coolest one. Sub 50 here and apply. Okay, once again, you can see our turbulent wake behind our cylinder. Let's shut our vectors off and get a closer look at this guy here. Very cool. Let's look at our pressure and apply that. Pressures always seem to look the same. Pressure's out in front of the cylinder, the highest pressure, and the lowest pressure is always behind. Okay, all right. Let's move on to our last one here. Let's go back to Workbench. And our last and final Simulation will be with a Reynolds number of 500,000. This is going to be very turbulent. Let's go to setup. Precision 4 and start. Okay, for this one, Reynolds number 500,000, we're going to have a velocity of 40 meters per second. Our viscosity is going to be 8 times 10 to the negative fifth. So very, very low viscosity. And our viscous model is going to be turbulent, so we're going to use standard capsulon. For that, again, our materials will use air. Air density will be at 1 kilogram per meter cubed, and our viscosity will be at 8 times 10 to the negative fifth kilograms per meter second. Okay, boundary conditions. Once again, velocity inlet. Let's edit this. We're going to be at 40 meters per second. I'm sorry, our velocity is at 40 meters per second. And we'll apply here, close. And again, come down here to reference values from velocity inlet. Everything here looks good, 40 meters per second, 8 times 10 to the negative fifth. There we go, methods. Okay, we want to go second order, upwind. I think the rest of these can be good. Okay, and report definitions. Of course we do. We like to, once again, report our drag forces, our drag coefficient, print to console. Okay. Close. Let's go down here to initialization. Once again, 25 and iterations. Okay, initialize. Run calculations. 500 again. And this is extremely laminar. This may take quite a while. So we'll run these calculations and we'll just get it going here. You can see it's already starting to get a little crazy. And it looks like it's going to take quite a while. So I'm going to pause the video. And our calculations are complete. Go to here. Okay, let's look at our report definitions here for our wall. Let's compute. Okay, we have a drag coefficient of 0.325 or 0.326. Let's go look at our forces again. And our forces on our wall, print these out. And it looks like we have a drag force of 260.79 newtons. Okay, let's go back to Workbench. Let's look at our results. Let's look at some streamlines, some vectors, and some contours. Here we go. All right. This out of the way. Streamline 1. Velocity inlet. It's about 100 number of points. And apply. And extremely turbulent, not a lot going on. Just air passing right around our cylinder. Let's look at the vectors. In here, symmetry 1. And apply. Wow. Okay. You can see a lot of our turbulent separation is very, very turbulent on the outsides here. Very high velocities. You can see where it comes the the airflow comes back for a split second just to be turned right back out. Let's look at our contours. And this will be symmetry 1. Velocity, we'll go 750 again. And apply. Okay. This is what our velocity looks like here. Let's turn off these vectors. Not bad. Not bad at all. Let's look at pressure. And apply. Once again, pressure always looks the same. Let's look at, you throw vectors in there. Oh yeah. This is our pressure with vectors added. And you can see that rotation of that vortex. It comes back in again. Then it all comes out the backside. Very cool. Very cool. All right. Well, there's your 5 simulations with 5 different Reynolds numbers for Ansys Fluent project number 3, flow over cylinder. Thank you very much. Have a great day.